Hi. So chapters or sections 10.2 and 10.3, I'm going to go ahead and do these together as one section because we're going to be using the TI-84 to make the calculations, and the TI-84 does both of those together. The reason the book separates it into two pieces is because they use the formulas, which we're not going to do. And when you see the formula, you realize why we're not going to do that. So the idea of linear regression is that you have pairs of data. This could be something like you ask somebody or you measure their weight and their height. And you're trying to see, as you go from person to person, is there some type of relationship between somebody's weight and height? Well, if you were talking about anybody throughout the United States, any adult throughout the United States, there may not be a strong relationship because there are plenty of people that are tall and heavy. There are plenty of people that are tall and very light, and the other way around. Some people are very short and heavy or short and light. But that's the idea. We're trying to see, is there a relationship? So here's a couple of examples that don't have any numbers. This is just opinion. What do you think? So do you think there's a direct relationship between, okay, now narrow it down to just newborn babies. Is there a relationship between the weight and the height of newborns? Well, for this, I would think yes. In general, the height and weight would be related. A baby that has gone to full gestation of 40 weeks perhaps is going to be bigger, had more chance to grow. A child that's born 2 weeks early is going to be not only shorter, but way less. So I think that in general, yes, there probably is a relationship there. Now, if you're talking about the prices of homes, and if you don't talk about just one neighborhood, you just leave that part out, then I would say no, there is no relationship, because you can go to the middle of Oklahoma and get a huge home for not very much money. Try to do that in San Francisco, you can get a huge home, but it's going to be $23 million as a fixer-upper. But if you concentrate on just one neighborhood, is there a relationship? So if you narrow the neighborhood down enough that other factors like, oh, San Francisco is more desirable than the middle of Oklahoma, sorry to all my Okie relatives, but it's true. Then if you're just talking about one neighborhood, then most likely, yes, there's going to be some type of relationship. The bigger the size of the house, the bigger the price. And what about hours of work and income? So this one, you might automatically think, yeah, if somebody makes $19 an hour, they work more, they get more. But there's a lot of people that are salary employees. And so, for example, right now, I'm working extra. I'm not getting paid anything to do this. So there is no relationship between my income and hours of work. So with this one, I would say, yeah, probably not. If you threw out all salary employees, then yes, there is probably a relationship. All right, so this relationship is called correlation. Is there a correlation between the two variables? So when you see correlation, that just means relationship. But by the way, we are not in this chapter going to be able to prove that even if we can prove there's a relationship, it's not cause and effect. So if for example, we say, yes, there's a relationship between the weight and the height, well, just because a child weighs more, does that cause them to be taller? No, because a baby could weigh more, they may have a bigger height, but it's not this weight that's causing the height. It's their genetics, what their mothers ate, how long they were inside the mom, things like that. Those are the things that affect the height. It's not the weight that caused the height to change. Okay, so we're going to be given, like I said, pairs of data, but now we're going to start talking about math. So we've got these pairs of data, X and Y. And in order to measure the strength of the relationship, so this being a math class, we need some type of numbers to talk about. So The test statistic is called the linear correlation coefficient. All right, hold on, here it comes. Look at this formula. Yeah, so this is the reason that we are going to be using the graphing calculator. But here's important facts about R that we will be using. One is the R was constructed so that it's always between -1 and +1. It can equal 1, but that means that there is a perfect positive correlation. That means basically you've got a line y equals 3x plus 1. So that means the slope is 3, and every dot is on that line. It's perfect. There's no dots that are off of the line even by a little bit. Then if R equals -1, it means there's a perfect negative correlation. So the difference between positive correlation and negative correlation is that positive means positive slope, negative means negative slope. One has a line that's going up, the other has a line that's going down. There's more about that coming up in the next slide. And then if R equals 0 or close to 0, that means that there's no linear correlation. Now this next slide has a lot on it, but it visually summarizes all of the possibilities. So look at this. Maybe you don't have R equals 1, but you have R is equal to 0.98. So here is the line. It would have a positive slope, and the dots are going to be all either on the line or very close to the line. So this is a very strong correlation. Also notice that as x gets bigger, then y gets bigger. So with a positive correlation, the two variables will do the same thing. If x gets bigger, then y gets bigger. Let's say that R equals a 0.50 or something like that. So in general, there is this trend of the dots going up, but it's not a very strong relationship. The dots aren't really falling on the line. They're a little bit scattered, so that would be called like a weak positive correlation. And then suppose that the dots are just random. Completely random, that means R equals 0. Or down here, it could be that there is a pattern. This is a parabola. But the thing is, in this section, we are testing for lines. We're looking for lines. So if you were trying to find a line, one line that goes through there, it's not going to happen. And then lastly, negative correlation. So negative correlation, the word negative just means that the slope is negative. It's not saying it doesn't exist. It's saying the slope is negative. So look at this. If x gets bigger, then the y gets smaller. So the negative correlation means the x and y do the opposite. As one goes up, the other one goes down. And then it could be that they are scattered, so there's a weak negative correlation. Okay, so that R that I was telling you about has to land between -1 and +1. So this is basically how we use the test statistic R. We will look up critical values in table A5. You'll put them right here. They're going to be things like 0.365 or 0.582. So once we get an example, you look at the R and you see, does it land over here to the right? If it does, there's a positive linear correlation. If the R lands over here to the left and it goes past the critical value, then there's a negative linear correlation. And then, if it's in the middle, this is like fail to reject. We are not able to prove anything. You just stop right there and say, there is no linear correlation. Okay, now we need to talk about that line. So, as you may remember from algebra, y equals mx plus b is the equation of a line. So, here are two possibilities. You've got a positive correlation or perhaps a negative correlation. Like I said earlier, positive correlation means that the two variables do the same thing. If x goes up, y goes up. So this would be, for example, if somebody is making $20 an hour. If they work more hours that week, they're going to make more money. If they work less hours, they're going to make less money. So that's positive correlation. Negative correlation means the two variables are doing the opposite. So it could be negative correlation. Let's see. It could be that the more I want to do something funny like bacon. The more bacon you eat, then in general, your physical health goes down. Okay. Anyway, these graphs, these little dots with the red dots, these are called scatter plots. So you're looking to see how are the dots scattered. And on our calculator, instead of using y equals mx plus b, they use ax plus b, where a is the slope. In this case over here, the a would be positive, and in this case over here, the a would be negative. But that's called the regression equation, y equals ax plus b. All right, now let's get to the first example. So this first example doesn't have a story behind it. Let's just use numbers that I made up and see is there a positive correlation or not. So, sorry to blast that right in your face, but you type in the data in list 1 and list 2. And then if you go to stat plot over here on the left, so second stat plot, turn it on. This is the scatter plot. Make sure it says list 1 and list 2. You have a choice of which mark you like to use. I like the little plus to keep things positive. And then go to zoom right here, zoom number 9. And this is what it would look like. So you can see that that looks like a strong positive linear correlation. And when you're asked to draw it, it should look something like this. So you don't have to put every little tick mark over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But you should give some general, so 1, 5 was one of the pairs, 6, 15, 12, 27. And I just drew, based on this, I tried to make my graph look basically the same. Okay, the next thing to do is you go to stat and then calculate and move down to linear regression. So right here you can see they're using ax plus b instead of mx plus b. Then if you've got an older calculator, it will not look like this. It will just say linear regression when on the screen and you just hit enter. With the newer operating systems, you put list 1, list 2, so that would be second 1, second 2, and then go down here to calculate. And no matter what, it should look like this. By the way, if the R is not there, then look at the bottom of the calculator and put second catalog. Go through the list and find the word diagnostics on. Hit enter for diagnostics on, and that will make sure that the R and R squared show up from that point on. So what I like to do is write down this information. So basically this right here is one section, and this is another section. So 10.2 and 10.3, but we're doing it all at the same time. So write all of it down. So the regression equation, write that down. And then the sample size, which I just went over here and counted n equals 12. And the R turned out to be 0.997. So that's almost a perfect positive correlation. Next, we need to use the table. Table A5 is the critical values for R. It's the easiest table we've got. All you need to know is alpha. So in here, in the directions, I didn't say what to use. We're using 95% level of confidence. That means use 0.05 here. And it's not even degrees of freedom, it's just whatever n is. So that means that it's 0.576. So if there's 0.576, this R lands way over here, and so there is a positive linear correlation. All right, then a real numerical example. So these biological twins happen to be separated at birth. Psychologists found them with their teams, and they tested their IQ. So they were raised apart, raised by different families. Biologically, they were identical. And the psychologists want to know, is there a relationship? So test for a linear correlation between their IQs. So here would be one twin, and then the brother or the sister, their IQ. Another twin, here's the brother or the sister. So you type all of the data into list 1 and list 2, Meanwhile, I'm going to get the critical value. So this was n equals 13, and again I'm using 0.05. So 13 and 0.05 is this one, 0.553. So you put that on the table, and the negative of it on the left. And like I said, type the data into list 1 and list 2, then go to second calculate linear regression. This is what we saw before. And then we need to write down all of this information. So R is equal to a 0.94. The sample size is 13. And I should write down the regression equation right now before I put the calculator away. Okay, there it is. Got it. Okay, so as you can see, this R 0.94 goes over here. That means that, yes, there is a positive correlation. As an IQ goes up, so here, as you go from one person to another, if this goes from 98 to 102, this goes from 97 to 104. So if this one goes up, then this one goes up. Positive linear correlation. Okay, there's one last thing. We haven't really used the regression equation. So the keyword that they would use, or we would use, is predict. So suppose you knew the IQ of the first twin was a 110. Predict the IQ of the second twin. Well, pretend for a moment that there was no linear correlation, that R turned out to be 0.01 or something like that. Well, then you can't use the regression equation because there is no correlation. So instead what you would do is just go to list 2, find the average, and use that. But in this example, we found there is a positive linear correlation, so we're allowed to use the regression equation. So there it is again. Then all you have to do is substitute the 110 for x, get out a calculator and find out the answer is 109.73. So there's section 10.2 and 10.3, regression. We've only got one more section and we're done with chapter 10. These last chapters are small. All right, see you soon.